Hello everyone, in this video I am going to explain optical isomerism. Geometrical isomerism, optical isomerism, both are configurational isomers. Configurational isomers two types, they are geometrical isomers and optical isomers. So in this video I am going to explain optical isomerism, optical isomers. So what are optical isomers? Compounds which have same molecular formula same, that means same number of atoms. So same number of atoms are present. The carbons are 3 and hydrogens are 6, oxygen is 1, like that. So molecular formula same and two molecules have same molecular formula. Same structural formula means atoms linked in a same order, bonding between atoms in the same order. So same bonding between, that means here it is if ABCD type, this is also ABCD type. For example, if you write this one, so H and this is OH and CH3, then it become 2 oxygen. Okay, here CHO, OH, H and CH3. Molecular formula same for both. Molecular formula same and bonding between atoms also same. But what is the difference? Compounds which have same molecular formula, same structural formula, same bonding between atoms in the same order, same. So the carbon with OH, carbon with H, carbon with OH, carbon with H, above CHO, below CH3, same bond order, bonding between atoms in the same order. So what is the difference? But differ in behavior towards plane of polarized light. They are differ in behavior towards plane of polarized light are said to be optical isomers, and the phenomenon of existing optical isomers by organic compound said to be optical isomerism. So if a compound show optical isomer, that is said to be its optical isomerism. Compound showing optical isomerism means compound exists in different optical isomeric forms. Okay, so what are optical isomers? The compounds which have same molecular formula, same structural formula, same arrangement of atoms, but differ in behavior towards plane of polarized light are said to be optical isomers, and the phenomenon is said to be optical isomerism. So what is plane polarized light? So this is one type of setup which is observed in polarimeter. All this setup we can observe this type of setup in polarimeter. So this is polarimeter. Polarimeter is instrument used to determine optical isomerism. Polarimeter. So in polarimeter there is a light. This is sodium light. Sodium light has a wavelength, particular wavelength. When it is passed through nickel prism, not nickel, this is nickel prism. Types of prisms, different types of prisms are there. In that, this is nickel prism. So when this light is passed through nickel prism, it become a plane. It become like a plane. Plane means, so like this. All the light passed in the form of a plane. That is called plane polarized light or monochromatic light. Plane polarized light or monochromatic light. Plane polarized light or monochromatic light. When this light fall on some optical active compound, any optical active compound, this is polarimeter cell. It is just a transparent glass tube in which the compound is taken. Which compound? Whose optical activity we are going to determine. That compound taken in this polarimeter cell. If this plane of polarized light rotate in anti-clockwise direction, this is clockwise direction, this is anti-clockwise. From this view, if light rotate in this direction, clockwise direction, such optical isomer is called dextroisomer. If light rotate in counterclockwise direction, anti-clockwise direction, that is said to be levoisomer. That means just like cis and trans isomers, E and Z isomers, syn and anti-isomers are geometrical isomers. All these are geometrical isomers. Cis and trans isomer, E and Z isomer, syn and trans isomers are geometrical isomers. In the similar way, dextro and levo isomers are optical isomers. If a compound rotate plane of polarized light in clockwise direction, that is called dextroisomer. If a compound rotate plane polarized light in anti-clockwise direction, that is said to be levoisomer. See this? The optical isomer which rotate plane of polarized light, either it is clockwise or anti-clockwise. If it rotate plane polarized light, that is said to be optical isomer, optical active compound. So the optical isomer which rotate plane polarized light in clockwise direction is said to be dextroisomer. That is said to be dextroisomer. Dextroisomer denoted with small d, English alphabet, or plus. Optical isomer which rotate plane polarized light in anti-clockwise direction is said to be levoisomer. Levoisomers are denoted with small l or minus symbol. They are denoted with small l or minus symbol. Thus, dextro-levoisomers are optical isomer. One can rotate plane polarized light in clockwise direction. Levoisomer rotate plane polarized light in anti-clockwise direction. If a compound rotate plane polarized light, that is optical active compound. Okay, right. Take this one. Next, organic compounds which rotate plane of polarized light in polarimeter are called optical active compound. Which molecules can rotate plane polarized light? Or which molecules show optical isomerism? Or which compounds are optical active? To show optical activity, compounds must have following character. Criteria to show optical activity. What is the criteria to show optical activity? Molecule should have at least one chiral center. Molecule must be at least one chiral center, or maybe more than one chiral center also. So at least one must be present. Molecules which should have non-superimposable mirror image. Non-superimposable mirror images. I will explain. Next, molecules which should not possess any element of symmetry. Any element of symmetry. Center of symmetry, axis of symmetry. So any plane of symmetry. No symmetry is present. Symmetry should not be present in molecule. Only such molecules are optical active. Three points. So what is the criteria for optical activity? Compound should contain at least one chiral center. Compounds should have non-superimposable mirror images, and compounds which should not possess any element of symmetry. I will explain all these three. So in that first, what is chiral center? What is chiral center? See the carbon atom which is directly attached with four different atoms or different groups. Whenever carbon atom directly attached with four different atoms or different groups, it is said to be chiral carbon or chiral center or asymmetric center or asymmetric carbon. Chiral asymmetric. Remember these terms. For example, glyceraldehyde. In glyceraldehyde, this carbon is chiral carbon, chiral center, because on left hydrogen, right hydroxy group, top CHO group, bottom CH3. Four different groups. So this is what? Chiral carbon or asymmetric carbon. So here this carbon is also chiral, because on this side methyl, on this side CH2, CH3. This is CH3, this is CH2, CH3. Different, this is chlorine. Here for this carbon, 3 bonds are present, mean other is what? Hydrogen. Other is hydrogen or not? Yes, other is hydrogen. So this is also chiral carbon. In bond line formula, we do not write hydrogen atoms, carbon atoms. So here 3 bonds are present, means in this bond line formula, other is what? This is what? Chiral carbon. So 3 bonds are present mean other is hydrogen, methyl, chlorine, ethyl, or 4 different groups. So this carbon said to be chiral carbon or chiral center. Okay, take this one. Do not contain any elements of symmetry. So molecule do not contain any elements of symmetry, may be optical active. Okay, so any elements of symmetry mean, so plane of symmetry should be absent in the molecule, and axis of symmetry should be absent in the molecule, and center of symmetry should be absent in the molecule, inversion also absent in the molecule. Only such molecules show optical isomerism. So what is the plane of symmetry? Plane of symmetry should be absent. First of all, what is the plane of symmetry? It is imaginary plane which is passing through the molecule in any direction, but which divide the molecule into 2 equal halves, such that one half is exactly mirror image to other. Such symmetry is called plane of symmetry. So what is plane of symmetry? It is imaginary plane which divides, which is passing through the molecule and which divides the molecule into 2 equal halves, such that one part is exactly mirror image to other. So for example, if I take this molecule 1,2 dibromo 1,2 dibromo butane, 1,2 dibromobutane. In this molecule, I am placing a plane. This is the plane. This is the plane which cut molecule into, which divide the molecule into 2 equal halves. Above of mirror image to below of. When you see this one, if it is mirror, above of is exactly mirror image to below of. So this is plane of symmetry. Molecule divided into 2 parts. So symmetry is present. Symmetry in terms of plane of symmetry is present. So if plane of symmetry is present, compound is optical inactive. Optical inactive because of plane of symmetry. Optical inactive because of plane of symmetry. Next, other element of symmetry, that is center of symmetry. Center of symmetry. What is center of symmetry? It is the imaginary point. It is the imaginary point when lines are drawn through it. When lines are drawn through it, they meet similar atoms or groups. Similar atoms or groups. So it is imaginary plane which is present in the molecule. For example, I am taking cyclobutane. This is cyclobutane molecule. Cyclobutane molecule. So here I am taking methyl group, hydrogen, methyl group and hydrogen here. Here hydrogen and methyl group. Here chlorine and hydrogen. Here hydrogen and chlorine. In this situation, molecule possesses center of symmetry. Center of symmetry, because if I draw lines through this point in opposite direction, when lines are drawn through it in opposite direction, they meet similar groups. It is imaginary point when lines are passed through it, lines are drawn through it in opposite direction, lines are drawn through it in opposite direction, they meet opposite direction, they meet similar lines, they meet similar lines. So if through this point, if I draw lines, so in this direction to this opposite direction is this one, hydrogen, hydrogen. Or if you draw lines like this through this methyl, methyl, here also hydrogen, hydrogen. Center of symmetry. Molecule said to contain what? Center of symmetry. Due to presence of center of symmetry, this molecule is optical inactive. Elements of symmetry should be absent to become optical active, but here center of symmetry is present, here plane of symmetry is present. These molecules are optical inactive. Next elements of symmetry is, take this one. Next elements of symmetry is axis of symmetry. Axis of symmetry. Third one is axis of symmetry. For axis, plural form axis of symmetry, or in singular form axis, axis of symmetry. Axis is the imaginary line which is passing through the molecule. Axis is imaginary line, which is passing through the molecule, which is passing through the molecule by rotation about which by rotation about that axis, about which molecule gives same appearance, similar appearance, or same appearance more than one time. Is said to be axis of symmetry. Axis of symmetry. See this. For example, if you take one paper or one card, any card. So if I pass a line through it by 180 degrees, it will give same appearance. After 180 degrees rotation, same appearance. Again by rotation 180 degrees, here 180 degrees, same appearance. That means about of 360 degrees, same appearance 2 times. Paper, this side, again same side. So here 180 rotation, here to here 180 rotation, here 180 degrees rotation, here 180 degrees rotation. Total 360. In 360 degrees rotation, same appearance how many times? So first time same appearance, second time same appearance 2 times. By rotation about which 360 degrees, by rotation about which 360 degrees, the molecule gives same appearance more than one time. So here 2 times. By rotation about this line, 360 degrees, same appearance more than one time. Here 2 times. So this is called C2 axis of symmetry. C2 axis of symmetry. C2 axis of symmetry. Okay. Another example, if I take another example, C3 axis of symmetry. C3. For example, if I take BF3 molecule, it has trigonal planar shape. If I pass imaginary line through boron like this, so BF3 molecule is like this, by rotation about 120 degrees, this is imaginary line, like this. Remove this fluorine comes here for 120, by 120 this fluorine comes here by 120, about of 360 3 times it will give same appearance, or otherwise see like this. If you see some okay, if you pass imaginary line through it, so by rotation about it, 3 faces are present, vertically 3 faces, back face, this one face, this one face. So by rotation 120, same appearance, by rotation again 120, same appearance, by 120 same 120 120 120 360. In 360 it give same appearance 3 times. Okay, so BF3 molecule is also same. Or by rotation about of it, same appearance 120 degrees same. After 120 degrees, this molecule again comes here, same appearance, again 120 same appearance, again 120 same appearance. So then molecule said to contain C3 axis of symmetry. C3, that C3, C2, C4 axis of symmetry. This contain which symmetry? C3 axis of symmetry. C3 axis of symmetry. Take this example. Square planar shape. By rotation about this one. Here same appearance by rotation about this one, same appearance 360 angle, it give 3 times same appearance. It give in 360 angle, it gives same appearance 4 times. C4 axis of symmetry. Thus, if any axis of symmetry is present, molecule is optical inactive. So that means axis of symmetry should be absent, plane of symmetry should be absent, center of symmetry should be absent, then molecule may be optical active. So to show optical isomerism, molecule should not contain any element of symmetry. That is my point. Okay. So this is just a general explanation. What is the axis of symmetry? For the axis of symmetry, I have given this example. Okay. This is not a chemical molecule. This is just shapes. Okay. So molecules do not contain any elements of symmetry. Plane of symmetry, axis of symmetry, center of symmetry. Molecule should contain at least one chiral carbon atom. And molecule should contain non-superimposable mirror image. Its mirror image should be non-superimposable. So that is third point. So to show optical isomerism, what is the criteria? Molecules should contain at least one chiral carbon. What is chiral carbon? When carbon atom directly attached with 4 different atoms or groups, that is called chiral carbon. Non-superimposable mirror image means non-superimposable mirror image. Non-superimposable mirror image means, see, if non-superimposable mirror image, this is A, B, here X, it's Y. If you see its mirror image, right become left, left become right. In mirror, top is top, bottom is bottom. Okay, so it is object. This is mirror image. Mirror image. Which type of mirror image it should be? Non-superimposable. Non-superimposable means how to verify non-superimposability. Rotate this molecule 180 degrees vertically. 180 degrees vertically. Then what happens? Like this. 180 degrees not vertical, 180 degrees rotation. Like this. Then it gives Y comes up, this is X, B is the same, and A comes, by rotation about it, it comes here, X comes here. This is X. And A comes down, and B comes. By rotation, this molecule 180 degrees rotation. This one comes here, this one 180 here, this one 180 here, and this one 180 here. A comes down, B comes left, X comes right, okay, Y comes up. So if you place this one, they are in exact alignment with each other or not? Exact alignment with each other. Now this can called. This image is 3, this is 1 is object, 2 is mirror image, 3 is someone. If 3 is exactly aligned with if all the atoms in 3, if all atoms in 3 exactly aligned with atoms of 1, then 2 is said to be non-superimposable mirror image. It's some complex concept, but necessary to understand. Not superimposable mirror image. 2 is mirror image or not? Yes, 2 is mirror image. So see this one. So this is some object, it's a molecule. Right, it's a mirror image. In mirror, top is top, bottom is bottom. But left become right. If you stand in front of mirror, your top is top only, head is top only, your legs are bottom only, but right hand appears left, left hand appears right. So top is top only, bottom is bottom only, but right comes left here, left comes right here. Okay, this is mirror image. Object, one is object, objected, one is object, two is mirror image. Or one is some molecule, one is some molecule. If consider this is molecule, two is its mirror image. Now verify mirror image is superimposable or not. So how to verify mirror image is superimposable on original molecule? Just rotate about of 180 rotation, 180 degrees rotation. So this comes here, put this one 180 rotate, left right, left comes right, right comes left, top comes down, down comes top, like this. Now if you place this one on this one, if they are aligned with each other, now this mirror is said to be non-superimposable mirror image. This mirror image said to be non-superimposable mirror image. Such molecules only optical active. Okay, so in next examples you will better understand, but try to understand more extent here only. Okay, non-superimposable mirror image concept means in this one. So mirror image by 180 rotation, if you place it here, if all atoms are aligned, that is said to be then this molecule said to be it has non-superimposable mirror image. Then this, in this case, this molecule said to be yes, this molecule has non-superimposable mirror image. But here if you place here, down is A but Y is here. If this is Y, if you place here on below Y, A comes here, below Y A comes here, below A Y comes here, but below Y, below B, B only, below X, X only. So here A, Y are not matching, not aligned, and A, Y are not aligned. That's why this is non-superimposable. This is what? Non-superimposable. Such molecules may show optical isomerism. That's the concept. Okay, next few terms regarding optical isomerism. They are enantiomers, diastereomers, mesocompounds. Enantiomers, diastereomers and mesocompounds. What are enantiomers? Enantiomers. Enantiomers are the optical isomers, which are non-superimposable, mirror images, to each other, are called enantiomers. Example, glyceraldehyde. I am taking glyceraldehyde. So marker completed. CHO and OH here, H here, and CH2OH. Its mirror image, M is mirror. Right become left, left become right, but top is top only mirror, bottom is bottom only. This is molecule. Okay, if it is optical active, its mirror image not superimposed. Molecule, this is what? Mirror image. Then verify for its superimposability. So to verify superimposability, 180 degrees rotation. Then right comes left, left comes right, bottom comes up, and up comes bottom. If you place this one, superimposed or not? Not. CH2OH here, CHO here. Of course, right OH, left H, okay. But here bottom CHO, here bottom CH2H. Non-superimposable. 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 The mirror image is not superimposable. That's why this is optical active. Therefore, above molecule is optical active. Above molecule is optical active. Above molecule is optical active. Okay. Right. Next, what are enantiomers? Optical isomers which are non-superimposable mirror image. Why it is optical active? So chiral carbon HU, OH, CHO, CH2, 4 different groups chiral. So optical active, and its mirror image is non-superimposable. Second character is also okay. It do not contain any symmetry. Third character is okay. That's why this is optical active. Next, diastereomers. Take this one. This example is glyceraldehyde molecule. Example is glyceraldehyde. This is D-glyceraldehyde, this is L-glyceraldehyde. Both molecules are non-superimposable mirror images. So, write like this. This is D-glyceraldehyde, D, R plus glyceraldehyde, and this is what? L-glyceraldehyde. Optical rotation determined practically. So in polarimeter, if it rotate plane polarized light clockwise, dextro. If it rotate plane polarized light anti-clockwise, levo. That is determined practically, not by looking at formula. So if one is dextro, other must be levo. Enantiomers. Next are diastereomers. So what are diastereomers? Diastereomers are the stereoisomers which are not mirror images. Diastereomers are stereomers, non-mirror images, which are not mirror images to each other. Are called the stereoisomers which are not mirror images to each other are called diastereomers. Example. If you take this molecule CHO, OH, H here, H, OH here, and CH2, OH. This is one molecule, and here these two molecules. Comparability, these two are mirror images. These two are what? One is D, other is L. If you see, they are mirror images, and it is non-superimposable. How to verify? By rotation about 180 degrees. So next, if you see this molecule, these two are diastereomers. Here H here, OH here, OH here, H here, CH2OH. See this one? So mirror image, are they mirror images? CHO, okay. Right here, okay, right here. These two are not mirror images. At this point, they are not mirror images. Okay, at this point, bottom is bottom okay, top is top okay. Here right become left okay, here left become right okay. But here right become right only. That means these are not mirror images. They are said to be what? Diastereomers. These two are what? Diastereomers. Okay. Erythrose and threose. Erythrose and threose are diastereomers. First molecule is erythrose. First molecule is erythrose. Erythrose. Second molecule is threose. Erythrose and threose are diastereomers. Erythrose and threose are diastereomers. Okay. Next, meso compounds. Next term, meso compounds. Take this one. How much time? Meso compounds means the compounds which have internal plane of symmetry. Internal plane of symmetry are called meso compounds. The compounds which contain more than one chiral center and internal plane of symmetry. The compounds which contain more than one chiral center and internal plane of symmetry. Internal plane of symmetry are said to be mesomers. For example, mesotartaric acid, COOH, OH here, H here, and OH here, H here, and COOH. Internal plane of symmetry, like this. So if you see this plane, above this plane, molecule is same or not? Above, below, same. Internal plane of symmetry. That's why this molecule is, example, mesotartaric acid. Mesotartaric acid. Okay, meso compounds are optically inactive. Of course, two chiral centers are there. See this one. I am writing this molecule again. Is this chiral carbon or not? Chiral. This is chiral. OH group, H group, COOH group, CHOH. COOH, CHOH. Different or not? Different. So chiral. Chiral carbon. So this carbon, H here, OH here, COOH here, CHOH here. Top is different, bottom is different. This is also chiral. Two chiral carbons are present but optically inactive. Two chiral carbons are present. Two chiral carbons are present. Two chiral carbons are present, but optical inactive. Meso compounds are optical inactive. Meso compounds are optical inactive. Meso compounds are optical inactive due to internal compensation. 1 minute. Okay, internal compensation means the above part to try to rotate plane polarized light in clockwise direction. At the same time, below part to try to rotate plane polarized light in and counterclockwise, anti-clockwise. So above part, below part, try to rotate plane polarized light in opposite direction. One try to rotate above part to try to rotate plane polarized light in clockwise direction. The same value below part try to rotate plane polarized light in opposite direction. One compensate with other, or otherwise if above one try to rotate plane polarized light in counterclockwise, below one try to rotate plane polarized light in clockwise direction. So thus internal compensation, this molecule become optical inactive, totally optical inactive. Of course, chiral centers are present. If chiral center is present in compound, the molecule should be optical active. But due to internal compensation, one cancelled with other, the molecule do not rotating plane polarized light in any direction. That means optical inactive. So meso compounds are optical inactive due to internal compensation. Two chiral centers are present but optical inactive due to internal compensation. Same molecule, plane of symmetry is present, above part clockwise, below part and counterclockwise. So like that, internal compensation. Meso compounds are optical inactive. Okay, next take this one. Mixture. What is the rhythmic mixture? The equimolar mixture of 50% dextroisomer, 50% levoisomer. 50% dextroisomer, optical isomer, 50% levo optical isomer. Equimolar mixture is said to be rhythmic mixture. So rhythmic mixture denoted with, it's a mixture of dextro and levo, so DL or plus and minus in bracket. Rhythmic mixture is optically inactive, even though optical isomers are present in which the mixture is optically inactive. So for example, the mixture of D-glyceraldehyde and L-glyceraldehyde. So D-glyceraldehyde is optical active. Individually it is optical active. Individually L-glyceraldehyde is also optically active. Levoglyceraldehyde is optically active. Dextroglyceraldehyde is also optically active individually. But its mixture 50% dextroisomer, 50% levoisomer. This mixture is optical inactive due to external compensation. Rhythmic mixture is optical inactive due to external compensation. So this dextroisomer try to rotate plane polarized light in clockwise direction. In the same extent, levoisomer try to rotate plane polarized light in counterclockwise direction. So both cancel with each other. That's why this mixture become optical inactive. This mixture do not rotate plane of polarized light in any direction. That's why optically inactive. Rhythmic mixture is optical inactive. Take this. Next, formula to calculate number of optical and mesoisomers. So in the similar way, number of geometrical isomers calculated by different formulas. Whenever alkene containing more than one double bond, we have used different formula to calculate number of geometrical isomers, 2 power n minus 1, 2 power n, like that. So in the similar way, optical isomers can also be calculated by using formula. So conditions: if compounds contain organic compound contain two similar ends, so two dissimilar ends. First, two dissimilar ends. If both ends are not same, both terminal groups are not same. Both terminal groups are not same means, see, for CH3, OH here, H here, and CH2, OH here. Here CHO, glyceraldehyde, I am taking example, glyceraldehyde. How many carbon? 1, 2, 3. Terminals are not same. One is CHO, other is CH2H. Thus, when terminal groups are not same, when compound contain two dissimilar ends, then formula number of optical isomers is equal to number of optical isomers is equal to 2 power n, and number of mesomers is equal to 0. Whenever two ends are not same, mesoisomers are not possible, because for mesoisomer, plane of symmetry mean top and bottom should be same. What are mesoisomers? The compounds which have internal plane of symmetry, compounds which have more than one chiral centers and internal plane of symmetry. So to have internal plane of symmetry, both ends should be same. Here both ends are not same, that's why mesomerism is not possible. Mesomers are not possible. Next, number of stereoisomers is equal to number of stereoisomers is equals to, so number of optical isomers denoted with small a is equal to 2 power n, number of mesomers denoted with small m is equal to 0, number of stereoisomers is equal to number of optical isomers plus number of mesomers, that is equal to 2 power n plus 0, that is 2 power n only. In this way, if two terminals of organic compounds are not similar, by using these formula we can calculate number of optical isomers, number of mesomers and number of stereoisomers. If compounds contain two similar ends, already completed, two similar ends. If compounds contain two similar ends with even number of chiral centers, even number of chiral carbons or chiral centers, even number of chiral carbons or chiral centers, both are same. What is then number of chiral centers? Number of chiral carbons or number of chiral centers. Okay, here n is equal to what? Number of chiral centers. If compounds contain dissimilar ends, this formula. If compounds contain similar end, then again two condition: even number of chiral center, odd number of chiral center. If even number of chiral center, then number of optical isomers is equal to number of optical isomers denoted with small a is equal to 2 power n minus 1. Number of mesoisomers is equal to is equal to, that is formula, m is equal to 2 power n minus 2 by 2. 2 power n minus 2 by 2. So even use 2. For odd here we use 1. So remember this formula, number of mesoisomers is equal to 2 power n minus 2 by 2. Total number of stereoisomers is equal to a plus m, that is equal to what? 2 power n minus 1 plus 2 power n minus 2 whole by 2. So these are formulae we use to calculate number of optical isomer, number of mesomers in a given organic compound. Thirdly, if compounds contain two similar ends with here even number of chiral center, here odd number of chiral center, if compounds contain similar ends with odd number of chiral centers or chiral carbons, then number of optical isomers is equal to number of optical isomers is equal to formula 2 power n minus 1 plus 2 power n minus 1 by 2. Okay. Number of mesomers is equal to 2 power n minus 1 by 2. Number of stereoisomers is equal to isomers is equal to, that means optical isomers plus mesoisomers, that is this one cancel or not? If these two are cancelled, then 2 power n minus 1. 2 power n minus 1. 2 power n minus 1. Okay, right? In this way, we calculate number of optical isomers, mesoisomers, whenever number of chiral centers are known. Okay.